I mean, we don't have a coffee break after this, so we don't need to end on time.
But we do.
We do, because people are going downtown.
It's even more tight, right? I'm motivated to end on time by coffee breaks. So we don't have one. So it's like 20-minute Q&A.
Yeah, I didn't lunch that. I was hoping at lunchtime. Correct. The processing is like fair.
You have to take your pick. Neither one's going to be on. Maybe that. Sir.
Yeah, I know.
Yeah.
I'm just getting ready.
All right, so welcome everyone back to the next session. Yesterday, we took together a journey into the deep depths of the earth and encountered arcane minerals, the names of which astronomers dare not utter. Okay, and so today we're going to take a spiritually similar journey into the world of Einstein's general relativity, sometimes abstruse and obscure, but we have a fantastic guide, world-renowned all-star erstwhile session chair, Haley McPherson.
Holy shit. All right. Yeah, like.
Now we're going to have to bleep this session.
Oh, I mean, oops. I mean, I am Australian. Anyway, what an introduction. Thank you. I feel like you should just give the talk. All right. Hi, everyone. I'm Haley. I'm Einstein Fellow at KCP at UChicago. And I am pretty deep into my final year. I think I've got like 3 weeks left of my fellowship, and so I'm really in reflective mode here today. So when I was preparing for this talk, and just the end of my fellowship, I decided to look back at my proposal to kind of see how I did. So this is kind of, laugh yet. This is kind of the opening page, paragraph, and the main research questions I wanted to answer during this fellowship. And obviously I will go into a lot more detail about what my field is specifically, but the kind of one-liner is that I'm interested in extending our cosmological modeling beyond the kind of current simplifying approximations that we currently make. So down here are my main research questions that I wanted to answer during this fellowship. And this first one here is like actually incredibly vague, and I think I will be answering that in some form for the rest of my career. So I don't really have a good concise answer to that one, but for questions 2 and 3 I do, and they are yes and maybe a little bit. Now these questions do have a bit of jargon in there that I'm going to need to go into a bit of background to help you understand what they mean. But my whole goal for today is to hopefully get everyone to understand what these 2 questions mean, why it's interesting to ask them, and hopefully what the answers mean as well. So in cosmology, we're really interested in these kind of big picture questions about the universe as a whole. And especially relevant today are these 2 questions: what is the universe made of, and how does the universe expand? Now it turns out these 2 are really quite intertwined, and if we can measure how the universe is expanding, we can learn something about what it's made of, and if we know what it's made of, we can say something about predicting how it's going to expand. And the reason for this is that, to the best of our knowledge, everything in the universe obeys Einstein's field equations of general relativity. And the left-hand side and the right-hand side really encompass these 2 research questions here. So the left-hand side, the Einstein tensor, tells us about the fabric of space-time, and so tells us something about how the universe expands. The stress energy tensor on the right-hand side tells us what the universe is made of. Or more formally, the Einstein tensor tells us about things like curvature and expansion, and the stress energy tensor tells us about the energy content, so things like matter, radiation, and dark energy. You weren't supposed to see that yet, but so now what we want to do is we want to use these equations to learn something about how the universe evolves, and to do that we have to put them into a kind of useful form. Unfortunately, when we do that, we very quickly arrive at something that is very complicated and difficult to apply in practice. So what we do in almost every area of physics that adopts general relativity, but especially in cosmology, we make some kind of simplifying approximation to the dynamical system that we're interested in to kind of make these equations a bit easier to deal with. And when we do this in cosmology, we end up with this instead. Now, the actual terms in these equations doesn't matter. All that's important is that it is much simpler than what I showed on the previous slide. And in getting here, we've made two key assumptions. The first one, which is the most important, is that the universe is both homogeneous and isotropic, or that it is exactly the same regardless of the physical spatial location in the universe, and the same in every direction that we look. This first assumption defines the Friedmann-Lemaitre-Robinson-Walker, or FLRW, class of models. And these models, combined with general relativity, is really the backbone of modern cosmology and is used in almost every single aspect, from our theory, simulations, and also all throughout our data analysis as well. So these equations are really, really important. The second assumption here is less important, but we have assumed that the energy content to the right-hand side of these equations is matter and dark energy. And so what I'm interested in asking in my research is this FLRW description really a good way to describe our universe? And to convince you that this is a reasonable thing to ask, I need to say a little bit more about this first assumption here, what it means and how it's actually employed in practice. So obviously we know that the universe is inhomogeneous because of the existence of galaxies and stars and planets and the cosmic web. We know that we don't live in a featureless fluid, like the Friedmann equations tell us. But what we can do is we can take galaxy surveys like this one here, and we can measure the scale at which this distribution of points becomes statistically homogeneous. And this is usually done using things like fractal dimensions that Sarah mentioned yesterday. And this is what's commonly known as the homogeneity scale in cosmology. And what we usually do is once we reach this scale of homogeneity, we say that the FLRW models are a good description for the dynamics of the universe. But this is the important bit. Just because the matter in the universe is statistically homogeneously distributed does not guarantee that the space-time beneath that matter is even close to being well described by these very simple FLRW models. My point here is just that this is an assumption that we make in cosmology that has not yet been thoroughly tested. And this assumption is literally as old as cosmology itself. So this was first implemented when we discovered the universe was expanding at all. And all that's changed since then is what makes up the right-hand side. So where the dark energy and dark matter, et cetera, exist. And I know that like assumptions and approximations of some kind are almost always required in all areas of physics to be able to do anything and extract any kind of information. But it's so important that we make sure that those approximations are not only valid in the first place, but also that their validity is sufficient for the precision of the measurements that we're using to constrain that model. So now I think we can go back and I can say a little bit about what these two questions here mean. So the first one, can low redshift anisotropy affect our cosmological inference? What I mean by low redshift anisotropy is small scale deviations from this very simple FLRW description of space-time. And so here I'm talking about at or around the homogeneity scale that we measure from the galaxies. So here I am assuming that at large scales our universe is well described by FLRW, but with low redshift data we very often play with redshifts very close to the homogeneity scale and also implement the FLRW model. And so I'm interested in seeing if whether inhomogeneities around this scale can impact our resulting parameter inference. The third question, does nonlinear structure formation have any impact on the global expansion? So here I'm really getting at the core assumption of lambda CDM, which is that once we reach this homogeneity scale, these FLRW models are a good description for the dynamics of our universe. So by global expansion, I just mean really, really large scales when we should be well and truly a homogeneous universe. Do the FLRW models actually describe the dynamics really well? And it's only quite recently that we've actually had the tools to be able to answer these questions without needing to either assume the FLRW models themselves or implement some other kind of really simplifying symmetries in our space-time. And so what we can do now is we can really do fully nonlinear general relativity in our cosmological modeling to really stress test these assumptions and see just how good they really are. And the tool I'm talking about here is numerical relativity. So you don't need to know much about this other than that it is a very, very clever computational method to solve that very complicated system of equations that I flashed up earlier in the talk without needing to simplify them to the other version that I showed. So this was originally developed to simulate binary compact object mergers like black holes and gravitational waves, but it's since been adapted to a bunch of other applications, including cosmology. So what this means is that we can simulate the collapse of the large-scale structure and the cosmic web without any of the kind of regular gravitational approximations that we make, like the FLRW model or even Newtonian gravity, for example. So now I'm going to say a little bit about how we address this second question here regarding low redshift anisotropy. So our steps are, number one, we simulate a universe using numerical relativity, which does not rely on the FLRW assumption in its evolution. And so that's something shown like this. This is the kind of cosmic web that we get out. Once that simulation is done, we place a set of synthetic observers in that simulation, and we use ray tracing to generate synthetic catalogs for them, something like a fake supernova survey for low redshift data. These observers then do exactly what we do with our data. We assume the universe is well described by FLRW, fit our parameters, and find something like the Hubble constant. But since we made the simulation, we can tell how it's actually expanding, and so we can see whether these observers get it right or how wrong they get it. So this is from a paper I put out in 2024, and this is showing the value of the Hubble constant that our synthetic observers infer in the simulation as a function of their local environment. So these ones live in underdense environments, these ones live in overdense environments. This dashed line here is the expansion of the simulation. The point is, the points don't lie on the line, and therefore there is some bias. The large points here are when these observers have a very isotropic distribution of their catalog across the sky. So they've kind of got a perfect survey that samples all directions evenly. The smaller points here are when they have a survey that is kind of patchy on the sky. So it's like missing spots. And this is actually made to mimic the Pantheon supernova catalog. Then what we can do is we can rotate this kind of patchy distribution to sample different parts of the sky, and that will affect their inference in the presence of inhomogeneities. The whole point I want you to take away from this is that, yes, we do see that our fake observers get their measurement wrong by up to a few percent, depending on where they live in the universe and how they sample their sky. So we've shown that at low redshift, we can get our inference a little bit wrong due to the presence of inhomogeneities. So what about at high redshift? What about this kind of global expansion? So when we're talking about the regime where we really should be homogeneous, and if within lambda CDM, we should be well described by these very simple models. So in this case, we are instead going to be constraining the cosmological density parameters. So these omegas tell us the kind of fraction of stuff in the universe. So for our favorite lambda CDM model, we have 30% matter, 70% dark energy, and 0 curvature, or a flat universe. And so the procedure for answering this question is very simple to the previous project, except now our observers have data that goes all the way out to redshift 3, and so they're really sampling the longest scales that we can in cosmology. Then they do the same thing. They use this data to infer parameters about their universe. And again, since we built the simulation, we can say whether these parameters that they infer are actually correct given the energy that we put into the simulation, right? Now, just to note, these observers live in a slightly different universe than lambda CDM. You can ask me why if you're interested. But if these observers get it right, they should measure a matter density parameter of 100% and 0 dark energy and 0 curvature. So this is a project being led by Sana Algamal, who's a PhD student at UChicago, and she's been playing with this ray tracing data and trying to constrain these parameters within the simulation for these synthetic observers. And so these are results for just one observer right now. The bottom line is that these observers are only biased by less than 1%. So this is a really, really small bias and is unlikely to be above the level of error bars for our surveys. I do just want to stress that this is not necessarily an obvious result, and this is actually the first time this has been constrained in a simulation and analysis framework that end-to-end does not assume the FLRW model or perturbation theory, for example. So this is quite a big result. And the reason that the answer is maybe a little bit here is because this work is still in progress. We have a lot of numerical testing to do, and also to see how this result varies between our different observers in the simulation. So this is something that Sana is working on right now. Okay, so in summary, yes, maybe a little bit. Both of those answers always come with an asterisk, as do any results that you see from a simulation. There are always caveats. But the bottom line is that general relativistic simulations are fun, and they could be really interesting and hopefully important for determining just how well our approximations in cosmology do against percent level precision surveys. And because this is the last words I'll ever say at this conference, I will say again, thank you very much to the program. It's been a lot of fun, especially meeting all of you and hanging out. So thank you very much.
have time for questions. I guess Raphael first.
Thank you very much. Very nice. Do you think that our location in the universe can affect the Hubble tension problem?
Absolutely. Well, it's not going to solve the Hubble tension, right?
No, not to solve, but I mean, is it possible to understand these inconsistencies between the different observables within the Hubble tension?
Yeah, so some people have looked at this with these kind of some exact solutions like LTB models, which just model kind of a symmetric void in the universe, right? And they say if you put us right in the middle of that void, you can get this a higher Hubble parameter if the void is, 0.5 underdense or something like that. I'm not sure exactly. But you can do that kind of in the context of like analytic models. And this is kind of why I did this study, is because I was like, this is a realistic universe that also takes into account the variance in space-time without the kind of symmetries in those analytic models. But unfortunately, as you can see here, the difference is only a few %. So it's not big enough to explain the full tension. But something like this is getting close to the level of the error bars in these kind of constraints. And so there's a bit more work to be done to see how it actually impacts our own surveys, but this is kind of an indication that, hey, we might need to care about this.
Yeah, okay, thank you.
Yes, do you want to ask yours and then come get set up?
Sure. So it seems like you're mostly concerned with inference, but like a big challenge in numerical relativity and CERN is convergence.
Numerical convergence?
Yeah.
Yep.
Simulations converge? Is that an issue?
They do. Yep. So that's incredibly important, and I never present any results that aren't converged.
Really?
So yeah, all of this always comes with at least 7 appendices. Please read them; they're excellent. And where various numerical studies and convergence is one of the big ones. So yeah, absolutely. Yeah. You got a mic? Sick.
Jumped to my conclusion. Oh, well, it's the tech check's fault. All right, I don't know how to work Keynote.
That's fine. Don't worry about it. All right, so that was a great
Start. And next, we will have a very exciting talk by Keith on black hole ringdowns.
Great. Well, for those of you who don't know me, I'm Keith Mittman. I'm an Einstein Fellow at Cornell, just starting my 2nd year. And I primarily focus on gravitational waves. Now, part of why I'm interested in gravitational waves is kind of the big thing that I'm curious about is understanding the theory of gravity in our universe. So as Haley said, right, we have this theory of general relativity, which for the most part explains the majority of our astrophysical phenomena. But fundamentally, we know that Einstein's theory can't be the whole picture. Specifically, general relativity isn't consistent with the physics we use to describe the microscopic realm, namely that of quantum field theory. So we know that this equation has to break down at some point. And you can try to understand how it might break down by just working through theoretical possibilities, but to some extent, we really want to let data guide us. And if we're going to let data guide us as to how general relativity might break down within our universe, a very promising place to look is through gravitational waves emitted by binary black hole coalescences. Now, the reason why is that if we want to probe deviations to GR, you really want to probe regimes of intense curvature. And so producing high curvature on Earth is relatively challenging. But if you think about the curvature that's produced when these 2 black holes coalesce, it's extremely high. And that information should get imprinted on the gravitational waves that propagate out. So if you want to look for deviations that are related to the curvature of space-time, they might be imparted on gravitational waves. And so this is kind of one of the first talks on gravitational waves. I'll kind of walk you through the basics of what these phenomena are. So whenever you have one of these coalescences, they emit gravitational waves, which can effectively be understood in terms of 3 morphologies. There's the inspiral, which is effectively perturbative. You can understand it with Newtonian gravity and some slight modifications and corrections. And then as the binary gets closer to coalescence, you enter the merger phase, which is where you need numerical relativity, namely taking Einstein's equations and solving them exactly on a supercomputer. And then after the merger phase, these 2 black holes combine to a single perturbed remnant, and that perturbed remnant rings down to a steady state by emitting energy in the form of gravitational waves in this phase known as the ring down. And so if you want to look for deviations to GR, you would naively think, well, maybe I should just look towards the merger phase. But the merger phase is really complicated, right? You need full numerical relativity, and so you would kind of need to simulate beyond GR theories if you wanted to compare deviated merger phases to actual data. And so a more promising place to look is the ring down, because whatever happens during the merger imprints itself on the ring down. And since the ring down is really just described by black hole perturbation theory, you can kind of use perturbative techniques to calculate what deviations you might expect based on certain beyond GR theories. And so that's kind of what I'm going to focus on for the rest of the talk. But before I do, I actually want some help from the audience. So does anybody know what this is? A spectrum, yeah. So this is some planetary nebula. I have no idea what it is. I know that these spectral lines correspond to certain things. So you have, say, doubly ionized hydrogen. But now I'm going to pose another question. Does anybody know what this is? So the last one was a planetary nebula at around 5,000 angstroms. This one has a little bit of a different scale, 10 to the 12 angstroms. Any guesses for what this might be? Okay, what if, bear with me, what if I told you that this was a black hole? Now you might go, well, Keith, black holes are black, they don't emit light, how can you have a spectrogram? Well, it turns out that black holes have very characteristic frequencies at which they ring when you perturb them. So this program is known as black hole perturbation theory. Effectively, the way to kind of probe this regime is imagine you have some Penrose diagram. And so if you haven't seen one of these, this is the black hole. Time goes in this direction, and space goes in this direction. So if I throw in some perturber represented by this green line, it'll cross the light ring. And when it crosses this light ring, it's going to emit radiation. And so since this is a very simple problem, you just have the Schwarzschild metric, you can solve for these perturbations exactly. And what you find is that there's 3 unique contributions, which tell you interesting features about the black hole. But when we think about the gravitational waves we observe from binary black hole coalescences, there's really one part of this signal that's important, that contains the majority of the signal-to-noise ratio. And these are these discrete frequencies known as quasi-normal modes. And so what these tell us is that when you have a black hole, the joke in our field is you typically say it rings like a bell, but in reality it thuds like a table. It just rings and shuts off. And the way in which it does that is through the emission of these quasi-normal modes, which are characterized by some complex frequency. So you really just have a sum of damped sinusoids, meaning the signal is incredibly simple. And if you observe a gravitational wave, it's very easy to search for these frequencies in your observation. The key part regarding these QNMs is that they come with these quantum numbers. So there's the L and M numbers describing the spherical geometry, just the usual spherical harmonics. There's this overtone index N, which when it's equal to 0 corresponds to the longest lived mode. And as you increase N, it just corresponds to faster damped modes. And then there's this index P, which corresponds to whether or not the mode is co-rotating or counter-rotating with the black hole spin. And so what's great about these QNMs is their frequencies is entirely determined by the black hole's mass and spin. This is effectively the no-hair theorem. And so what this means is that if I measure one of these complex frequencies, I can immediately recognize what the mass and the spin of the black hole are. And furthermore, if I measure the intensity of one of these frequencies, so the amplitude in front of this damped sinusoid, this is determined entirely by how I kind of perturb that black hole. So if it was formed by some binary black hole coalescence, the amplitudes of these frequencies directly encode the information of the progenitors. So it's to say, if I see a ringing black hole, based on the amplitudes of these frequencies, I can tell you what kind of black hole has produced it, or if it wasn't produced by merging black holes at all. And so that's where we get back to this spectroscopic picture, where here, what I was showing you is not just a black hole. This is actually a black hole from one of my numerical relativity simulations. And so if you know a bit about how these QNMs behave, you can actually start to identify which of these lines correspond to which of the QNMs. So the typical QNM we often see in data is what's known as the 2-2 fundamental. So it's the dominant mode of gravitational radiation, this 2-2 spherical harmonic, and it's the longest lived mode. And so if you measure this in data in some LVK observation, you can infer the mass and the spin of your black hole. This is known as black hole spectroscopy. But if you see 2 of these QNMs, each QNM should give you its own prediction of the mass and spin. And so you can actually pit these 2 inferences against each other to not only measure the mass and the spin, but if there's a potential deviation of the Kerr metric, right? If each of these QNMs predicts a different mass and spin that aren't consistent with one another, then maybe you've observed something that isn't a black hole, or maybe you've observed some theory of gravity that isn't general relativity. Furthermore, if you start to see many of these QNMs, such that you can measure their amplitudes and look at their relative excitations, as I said before, you can actually start to understand what might have produced this black hole in the first place. And so it's a common misconception that this 2-2 fundamental is the loudest mode that you always see. And so we actually had a paper where we studied numerical relativity simulations. And what we found is that of all the fundamental modes, of these n=0 modes, it turns out that the 2-2 actually doesn't need to be the loudest. And for certain types of binary configurations, you can excite, say, the 2-1 mode to be louder than the 2-2. And this typically happens for precessing systems, so black holes whose spins are misaligned with the orbital angular momentum. And so what this means, why it's exciting from an observational perspective, is that if you see these modes in your data, if you see a 2-1 that's louder than the 2-2, that effectively immediately tells you that the binary you observed was actually a precessing binary, which might tell you something about black hole formation channels and the nature of these binaries in terms of their general populations. But what has me really excited is that we're actually already doing this with data. We don't even just do this with numerical relativity simulations alone, but we can actually do it with real LIGO, Virgo, Cagra observations. So here, what I'm showing, this is just the first observation, GW 150914. You can see, it's clearly in the data, but there's still a lot of noise. The signal-to-noise ratio for this event was about 20-25. And it turns out that if you look at the very end, you can kind of see that this gravitational wave starts to come down like a damp sinusoid. And so in this event, you can actually identify the 2-2 fundamental. And because of that, you can do black hole spectroscopy, where you compare the frequency of this QNM to the mass and the spin that's inferred by the entire signal. And you can kind of test to see if the ring down is consistent with the full prediction from general relativity. But you may have seen this for the 10-year anniversary that we actually observed a recent detection, GW 250114, which is effectively identical to 150914, but it was 3 times as loud. And as a consequence, you have a very clean ring down signal. And so one thing that I just want to briefly highlight is that this signal is louder not just because it was closer or more massive. This is really a testament to the innovation of the detectors, because this improvement in terms of the SNR by a factor of 3 was purely governed by the technical advancements in the past 10 years. So it's really a testament to the advancement of gravitational wave detector science. And so I was fortunate enough to be on the paper writing team for the spectroscopic analysis of 250114. And so we found something pretty interesting. So here, this is a numerical relativity simulation of this event produced by my collaboration, the Simulating Extreme Spacetimes collaboration. And so if you wait until the merger phase, effectively what we want to do is we have this gravitational wave emission shown by the white lines, and we want to decompose it in terms of these quasi-normal modes to try to do tests of GR and maybe do kind of ring down inferences as to what the progenitors might be. And so what was really exciting about this signal is, like, unlike 150914, we didn't just see one tone. We didn't just see the 2-2 fundamental, which is this green, but we also saw the 2-2 overtone. And we even saw a third tone representing a higher order harmonic, the 4-4. And because of this, we can not only do typical black hole spectroscopy, but because we observed 2 frequencies, and really even 3, you can start to do tests of GR just based on the ring down. And so that's what this shows. Here, the black crosses correspond to the frequency and the half-life of the different tones that we observed, where the black crosses are calculated using the mass and spin inferred by the entire signal. The contours are the posteriors for these quantities, inferred from the ring down alone. And so the fact that you see that they all overlap means that GR is consistent. But you can see, there's kind of some hotspots. So maybe in another 10 years, these posteriors will start to converge away from these points, and we'll either have some evidence of systematics in our analyses, or perhaps a real deviation from GR. And so with that, I'll just say that while all of you may think the future is bright, I think the future is dark, and there's a lot to learn from gravitational waves. So thank you.
It does seem like it's getting louder.
Yes,
so it's exciting.
It's getting louder.
We do have some time for questions.
Yeah, it was interesting to see the dependence on, what it looked like the ring down depended on the line of sight to the direction of the spin of the black hole. So at some point, the merger and ring down carries away angular momentum that changes that spin, right?
Yes.
From here to whatever it is afterwards.
Yes.
So is that also imprinted on the ring down?
Yeah, so that would be, so you're talking, yeah. So, right, so
this description is defined with respect to a certain frame, so it's usually defined with respect to the spin of the remnant. But you're right, you'll have this merger, and then as the gravitational wave is propagating out, it carries energy and momentum. So that will change the mass and the spin of the perturbed remnant. So the changing of the mass and the spin is a second order effect. You have a gravitational wave coupling to a rotational wave. For that to couple back to the gravitational wave requires a third order effect. So we do expect that to be present, but it would require a third order black hole perturbation theory. And as of this past year, we've really just completed second order perturbation theory. So that would be kind of the next step in doing this perturbative approach.
Okay, so you think it's at high enough order that it doesn't affect this analysis?
Just with SNR first order relative to second order, there's very little SNR in second order. So we assume that there's not going to be much power in the third order effects. But they probably are.
Well, good luck with the third order.
Yeah.
Cool. Nice talk. Could you go to the slide where you had the contours?
I'm sorry, the contours. Yeah. Yeah, man. There you go.
Yeah, so in the first tone, that contour is so tight and it looks slightly offset. So I was just wondering what tension is there.
Oh, I mean, here it's not a real tension. Yeah, any observation here is completely consistent with GR being perfectly fine. You can't really make any conclusive statement about things being skewed.
What do you need to make these smaller? Is it like more super loud events or like even better detectors?
Yeah, so I mean, over the past 10 years, the improvements to the detectors made us able to see things 3 times louder. So the idea is we probably just need to keep improving the detectors. There's certain technologies we know of that we need to implement to kind of push up our SNR capabilities. But what we've kind of seen is that with these golden events, I mean, so 250114 constrain GR better than the entire prologue combined. So these single golden events are really what elucidate a lot of interesting physics, at least not on the population side. But in terms of testing GR, we kind of have to hope that we just get something really massive, really close, with insane SNR, and then we get to start doing something.
All right, so let's thank the speakers again. I just assume you're in charge now.
Yes, I will be. So hopefully we can get everything set up. All right, Nancy will be on time. Oh, there it is. All right. Hello, Nancy. Okay.
Oh, hello.
I'm going to be ready. I will introduce Nancy, and then we'll start. So it is my pleasure to introduce Nancy Hufek to you. This is our guest, and we are lucky to